Alright, for you guys doing lab, sorry, I'm eating popcorn while I'm doing this. Tomorrow, you're going to be doing a simulation of the lab that we would have normally done in class. And essentially, if you look at the document that I attached to you for you guys on Schoology, what you're going to see is that there's a hyperlink. You click on that hyperlink and it's going to give you a simulation where we have a level track, there's a mass, and what we're doing is we've got a force sensor that we are dragging to the right. So we apply a force to the right on this mass here, and what we get is when we do this experiment, normally we would put a motion detector over here, and it would detect an object's position as a function of time and also its velocity as a function of time. Now what this thing does is it accelerates to the right. So the corresponding position versus time graph that the simulation is going to generate is going to look like that, which isn't of much use to us. However, the velocity versus time graph is going to be of use to us, because what we could do is we can fit that line, we can get the slope of that line, and it gives us the acceleration. Now when you use this simulation, you're going to find that if you're working with your friends, the numbers might not correlate to each other 100% perfectly, because I think he factored in some sort of experimental error and also wind resistance here. So that might vary a little bit. But overall, the numbers should be pretty consistent, and there's no harm in using one person's numbers as opposed to another. And so you can always choose your force, choose your mass, and ultimately figure out your corresponding acceleration. Now, in part one of the experiment, what we do is we keep the same mass, but we vary the force. So we're going to make the force larger and larger and larger each and every time. So initially you'll start out with some sort of small force and step it up. And if the numbers are making conceptual sense, what should happen is that your acceleration should go up each and every time. And so we ask you to, I don't know if they're in this specific order, record the force, mass, and the acceleration for your trials, right? And obviously the mass is staying the same, so that whole column should match. I would encourage you to convert the mass to kilograms. It'll make a lot more sense if you do. No harm if you don't, but you've been warned. And then essentially this is an easy part of the simulation, because we ask you to do a graph here. And when you graph out the force versus the acceleration, a lot of people go, shouldn't I put force on the x-axis? You could. Your math teacher might demand you do. I don't. I actually like setting it up this way because you're going to get a linear relationship between the force and the acceleration in this scenario here. And if you fit that, if you've done it properly, the slope should be equal to the mass. Keep in mind, if you did not convert it to kilograms, you have to recognize that when you calculate your slope and do your comparison. But either way, pretty easy result, and this would confirm Newton's second law, which is F net equals ma, where you can see that basically what we're doing is we're taking our force, putting it on the y-axis, taking our acceleration, putting it on the x-axis, and this would be our slope, m. Now part two of the experiment is going to involve us choosing a force but increasing the mass each time. And you're going to do it more than this, but I'm only going to write 3 masses here, and you can't even see it right now. So what that is going to do is that's going to result, if it's going to make conceptual sense, in less acceleration as you step up the mass. And then what we want to do is, again, you're going to generate the same graphs, and you're going to have to analyze the v versus t graphs to get that data. But we'll make our columns here, F, M, A. Again, I don't know if they're in this order. Here might be even more useful to convert your mass to kilograms. And what you're going to find is that we're going to have a nonlinear relationship here, because as mass is increasing, the acceleration is going to go down. So we're actually going to obtain what we call an inverse relationship if we plot acceleration versus mass here. And what it's going to look like is something like this. As m gets larger, a goes down. And this is going to be an inverse shaped curve, which actually mirrors the graph of, like, so let's say 1 over x. And that's how an inverse relationship works. It says one goes up, the other goes down. And that's not really of any use to us, at least without the aid of a computer. If we had a computer, we could easily mathematically fit this curve. But what we want to do is fit it on paper. So you're going to take your data and modify it. We're going to try to linearize it. So I want you to make a column of 1 over m. And what that is going to do is if we plot a versus 1 over m, then we should get a linear fit. And let's look at the second law really quickly and see why. If I do sigma f equals ma, I want to relate a and m. So what I'm going to do is first off, I'm going to flip the equation to be that, and then I'm just going to divide both sides by m, and I'm going to write it as sigma f 1 over m. Now essentially what we're doing here is we are plotting our a data on the y-axis, or 1 over m data on the horizontal axis or the x-axis, and that would give us a slope equal to sigma f. So in this case, if we've done this properly, I would expect the slope here to equal the force. So if you can generate all three of those graphs and get a number that makes sense with the force value that you've chosen, you've done it all right. And I'm not sure if we'll submit this in person, because we might theoretically be back on Wednesday, or if we submit it online. Let's wait and see what happens. But for you guys in lab, this is what you're tasked with doing on Monday.